Right. How you right? Oh, taking it forward. Good. Okay. Rebecca, yeah, we produced an applied seminar after a few weeks of absence. This week from Doireann O'Kiely from Ireland, University of Limerick. She's going to talk to us about moving out of plane, buckling, and wrinkling.
Thank you. Great. Okay. So most people in this room do, apart from you, mechanics of some kind or another. Is that right? So just so I know who's fluidity and who's solidity. Got it. Okay, perfect. The talk as I've written it is more about solids than fluids, but we can spend more time on one slide than other, depending. And I'm not overly invested in getting to the end, so if you want to interrupt and take the talk on a chatty tangent, I'm fine with that. Okay, so I do applied maths about physical problems, unsurprisingly, and they fall into kind of two main categories. One is problems involving some kind of chemical reaction, so that might be batteries, that might be cleaning up toxic spill, and then the other half of what I'm interested in is the mechanics of thin sheets and how they form. So here are some examples of things that do that. So some of these are from research, some of these are just pictures for the hell of it. This is a very thin sheet of glass. This is polystyrene, paper, glass, honey, titanium on a polymer, self-explanatory, purely simulation, that's polystyrene, and this is an electronics circuit system. So the kind of big picture here is that thin sheets of fluid and solid and things in between buckle and wrinkle and can give you patterns and differently shaped surface profiles, and that can be advantageous for some applications. And so from a maths point of view, the kind of big picture goal is use maths to understand the physics of what's happening in some of these systems in order to improve your ability to do engineering. So what I'm going to do is I'm going to mention some specific examples of systems where I think about thin things deforming or have in the past thought about thin things deforming. And then I'm going to tell you about one in quite a bit of detail. So the first is metal forming processes, which you mentioned one of my PhDs thinks about. And this is joint work with him in UL and some people in Warwick. And so metal forming is one way of making metal shapes. So if you think about it, you can cast things in a mold, or you can take a big lump of metal and carve stuff out to make a desired shape, or you can take a metal and deform it into a desired shape. And that last version, that's metal forming. So one example of metal forming is sheet rolling. And I think of this as being analogous to rolling sheets of pasta. So you take a thick block of metal, you feed it in between some rollers, and it comes out the other side. Okay, so the goal of that process is to reduce thickness. There are various complications like work hardening, and if you want to, you can think about crystal structure and other stuff, but from a fundamental mechanics point of view, you're taking something planar, you're keeping it planar, but you're reducing its thickness. Okay, then by contrast, a different problem that we're starting to think about is metal spinning. And metal spinning is different because you take something flat and make it curved. So this one I think of being a little bit analogous to a pottery wheel. So you start with a flat sheet and you spin it around this axis, and then you push it gradually onto some target shape. And things can go awry when you do this, basically because you take something that was here, you push it radially inwards onto this shape. And when you do that, you can induce wrinkling or tearing or some combination of those things. And so that's just where that stage where the process goes awry is interesting for me, because if the mathematics can tell you what's happening, then it can tell you how to fix that. Okay, a second example of where you might think about changing the shape of thin sheets is glass and polymer drawing processes. So the first example is not actually a sheet, it's a thread. But when you're making something like an optical fiber, you start with a drop basically of molten glass falling out of a crucible, and then it falls under gravity and gives you a very long thin thread. And you can use this to make things like optical fibers. You can make your mathematical model more or less complicated depending on whether you think about temperature and rheology and various other processes, but from a deformation point of view, you're just trying to reduce the thickness or reduce the radius. And the same is true for some sheet manufacture processes. So there's this process called sheet redraw that I thought about back when I was a PhD student. And it's a way of making really, really thin glass sheets for things like smartphones. So the idea is that you take a block of glass whose dimensions are maybe something like what you would put in a window pane, maybe a centimeter thick, so a bit thicker, and you heat it up by feeding it vertically into a furnace. And then as it comes out the other end, you pull on it and stretch it. So you make it longer and you make it thinner. Okay, and you can think of an analogy if you want, where you take, I didn't bring many props, where you take something like a sheet of plastic, a bag or wrapping or a piece of rubber, and you stretch it. Okay, and in principle, it gets longer and thinner, but other things can also happen because you can induce wrinkling. And so this is a process where most of the time it works really well. You reduce the thickness while keeping something planar, but sometimes you instead get out of plane deformations, so you get wrinkles. And again, the question is, where did these come from? What controls them? What's the mechanics underlying their formation? Okay, so those are two examples of situations where wrinkles happen and it's undesirable. But wrinkles aren't always undesirable. So maybe I can skip forward and then back. Okay, so you can think of lots of different situations where wrinkling or buckling happens in an uncontrolled way or in an intentional way. So this metal spinning, that's unintentional. If you have something collapse or buckle, that's a support structure, that's bad. And I mentioned this stretched plastic. And again, that's typically not intentional. But there are situations where buckling or wrinkling is desirable. So if you are wanting to make a flexible electronics, so something like a wearable device, say you want a circuit that runs around a joint. Well, the issue is if you build a circuit with your arm flat and then bend your arm, you stress all of the components and you break the device. So what you can do is basically try and build in wrinkles a priori with a kind of accordion structure, so that when your arm is in this configuration, everything is just folded up nicely without huge stresses. And then when you bend your arm, you have the excess length that you need built in a priori. Okay, then other situations where you could use wrinkles to your advantage are things like optics, where you can use a pattern surface for wavelength selection or for deflecting light, or surfaces where you might use wrinkles to change wettability or to change just the amount of surface area for something like a reaction. Okay, so what I'm saying here is that sometimes it's about avoiding wrinkles, and then you want to figure out when they happen and just never do that. Right? But sometimes it's about controlling wrinkles. And from a modeling point of view, that's actually, I think, more exciting, because now you're saying, let's go into that interesting part of parameter space and actually dig around in it and try to figure out not just when does wrinkling happen, but with what wavelength and what controls that and in what direction, and what are the stresses post wrinkling and stuff like that. Okay, so the slide I slipped over was just kind of definition of what I mean by wrinkling. And this is pretty loose, okay? But if you think of all of the situations where you take a surface or structure, and you confine or compress it and it buckles. If it buckles with a very small scale compared to the system size, I would call that wrinkling.
Yeah, sorry, can you repeat
Yeah.
that because he is.
Okay. So, alas, I only have my jacket. Right, if I do this, I call that is a buckle.
Okay,
Okay, but if I have a very high wavelength pattern, that's a much shorter wavelength than the length of the sleeve, I call that wrinkling. Okay. Good, okay, so then in terms of modeling, you can start conceptually by thinking about an Euler beam. So, is everyone happy with an Euler beam? Yeah, okay, so you want to think about taking a beam, applying some compressive force and pushing the ends together. And then the question is, what does it do? So there's two options. It can get shorter and thicker, and that's always an option. But at some point it becomes energetically favorable for it to buckle instead. And so from a maths point of view, you have a force balance where you have bending with a bending stiffness, and then you have end shortening with a compressive force. And so the solutions of this, if your force is negative, are sines and cosines. So I'm just going to think about the sine solution. And if I want to impose particular boundary conditions, then I can only have non-trivial solutions for particular values of f. Okay, and so there's some critical value of f where you first get a buckling solution, and then beyond that you expect it. Okay, so that's your critical load, which you can calculate basically by differentiating that and sticking it in there. And one thing to say here is that there's many possible solutions, right? So you can buckle with a single sine curve, but you can also buckle with 2 or 3 or 4 or 5, etc., just by reducing the wavelength. So the way the system decides which configuration to take is based on energy minimization. Okay, so in this system, there is an energetic cost associated with bending the beam, which is a bending stiffness times a curvature squared. And so if you think about taking derivatives of this, you're going to minimize it by minimizing n. Okay, so you choose n is equal to 1, and in the real world, you only ever see a buckling solution that's just one sine curve. Okay, so if that's the case, then how do you end up with these wrinkling scenarios where instead of 1, you have very many small scale wrinkles? So the difference is that in those systems, there's a third effect at play. So instead of just thinking about a beam, oh no, guys, we're stuck. Right, instead of just thinking about a beam, let's think about a sheet of paper. Okay, and so before I can take my sheet of paper and push the ends together, can I actually steal a piece of paper? I think that would make it less easier. Okay, so I can take the ends and push them together, and I get my one buckle. If instead of having this as it is, I glue it to something, so I could put it floating on a liquid, I could glue it to something that's solid but still deformable, like my flesh. And if I do that, then when I lift the sheet, I also have to lift whatever is underneath. And so I have a competing force. Okay, so if I squish my arm, I don't just see necessarily one buckle, sometimes I see many small wrinkles. And that's because as well as deforming my skin, I have to also deform the flesh underneath. Okay, so now you kind of think maybe there's two energetic contributions. There's the fact that I need to bend my skin, and also the fact that I need to deform the skin, the flesh underneath. Okay, and I'm thinking about my arm because I have it here, but there are lots of much more controlled scenarios you can think about. And Joy Paulson and some others thought about some really nice ones almost 10 years ago now. So the kind of prototypical system you think about is you take a sheet of some elastic material, you put it floating on a liquid, and so you apply an end-to-end displacement. So you induce compressive force. That compressive force induces wrinkles. And the compressive force actually more or less disappears, which will be important later. But the thing to say now is that you're bending the surface, but also pushing up and down the substrate underneath. Okay, and that's basically a buoyancy force. So if you think about your force balance, you have a bending term like before, and a compressive force term like before, and then you also have a term that's substrate stiffness times vertical displacement. So if this is water, that would be rho g, for example. Okay, and you have to satisfy this force balance subject to some length constraint, and that length constraint says that whatever end-to-end displacement I impose, that reduction in length has to be accommodated by the wrinkles. So the wrinkles have to go up and down enough to account for the fact that I have reduced the total length. Okay, so the problem now is I can control delta, the end-to-end displacement, or I can control F, the compressive force, but I can't control both. So F is actually an unknown in this problem. And so if I think about my solutions, which are going to be sines and cosines, okay, and I think about substituting this into the force balance and figuring out what my possible solutions are, the problem is that F is still an unknown. So I have to, in principle, figure out what F is. And the way I do that is by having a second equation, which comes from my length constraint, which tells me that there has to be a relationship between the number of wrinkles I have and the height of those wrinkles. Okay, so if I have more wrinkles, then the amplitude will be smaller. And if I have fewer wrinkles, the amplitude will need to be larger. Okay, and then once I know this, then instead of thinking in terms of a force balance, I should think in terms of energies. So I now have two energetic contributions. I have bending times curvature squared, but I also have the substrate stiffness times how much I actually am shoving the material underneath up or down. Okay, and the idea is that if your solution is sines and cosines, then when you differentiate and substitute in here, you'll get something with, if m is my wave number, and m to the 4 in this one, but not in this one. And I have to minimize the sum of those two things. But both terms are also going to be proportional to the amplitude squared because I have a W squared. Okay, so I do some jiggery pokery algebra, which I'm not going to bore you with. And I end up saying that the energy I need to minimize is the sum of a term that increases with wave number and a term that decreases with wave number. And so there's going to be some compromise intermediate wavelength that minimizes the sum of the energies. And I can write that down. So I can write down a wave number and I can write down a wavelength. Okay, so that's what Joey and the others did. And then they did some really nice extensions where they thought about more complicated systems than just having a substrate. Okay, but the big picture idea, right, is that you have a competition between a bending stiffness and some kind of substrate stiffness. Each of those stiffnesses you can associate with a force and with an energetic cost. And then there's a preferred wavelength that minimizes the total energy. Okay, and so in the system we just thought about, you have what I would call a local lambda law. So wavelength lambda that minimizes energy locally. Specifically the energy associated with bending and with stiffness. And then they did these nice extensions where they thought about a system where there's some overall curvature in addition to the wrinkles, which gives you more stiffness, and systems where you have tension along the wrinkles, which is another kind of stiffness. Okay, and so you can, instead of just having a substrate stiffness, have a kind of effective stiffness that takes into account all of these restoring forces. Yes, please.
Why, maybe it might be a stupid question, but why the term associated to compression is not present in the energy balance equation?
Yeah, no, it's a good question and I skipped over it. So it's basically because of the length constraint. So are you a person who starts with energy more naturally or starts with forces more naturally?
I mean, I know it's a good question. I don't know.
Okay, so okay.
I think I like the way I think about this problem is I have an energy my energy functional that
Yeah.
somehow if I write I don't know some Hamiltonian equation I can following Hamiltonian formalism I can go to my equation of motion.
Okay,
That's
perfect.
how I would
Yeah. In that case, I would say the compressive force acts as a Lagrange multiplier. So you minimize the energy subject to a constraint that the total length
Yes.
is accommodated in these wrinkles.
Mhm.
And that constraint needs a Lagrange multiplier, and the Lagrange multiplier is the F. So in some roundabout way, it does appear in the energy minimization, but as a Lagrange multiplier, because you don't prescribe it, it comes out of the problem.
Okay.
Does that make sense?
Yeah.
Okay, nice. Well, we're paused. Does anyone else?
Sorry.
I was gonna ask if anybody else wanted to take the opportunity. Okay. How are we for time? Good. Okay. So kind of following on from those theoretical predictions, you need some experiments to help you validate. And the really classical experiment in this field is indentation of a floating sheet. So what you do is you get a sheet of some really thin stuff, which might be polymer or polystyrene or something else. You cut out a disc and you float it on water. And then you poke the middle of the sheet, which means you push material down and pull material radially inward. And because you pull material radially inward, you induce a hoop compression. And that hoop compression gives you wrinkles. Okay, so what you're saying is that if your sheet was radius 1, the stuff that was at radius 1 is now at radius 1 minus something. And so you've taken your material circles and squashed them. And that squashing means you have a compression and wrinkles. Okay, and this is really well studied. There's really nice theory, there's really nice experiments. The kind of overall takeaway is that you have some wrinkle wavelength once everything is static, which is determined by a balance between the bending stiffness of the sheet and the buoyancy and these other stiffness-like type effects like tension and curvature. And what you see both in your theory and experimentally is that as you increase the indentation depth, so the more you poke your sheet, the smaller the wavelength gets. Okay, so you poke more, you get more finer wrinkles. Okay, and so what we start to think about is, firstly, what happens when things vary in space, and also what happens when things vary in time. Okay, so I'm going to start with this second question: what happens when things vary in time? Okay, and so what I'm asking is, what happens if I think about systems like this? Well, instead of allowing everything to come to quasi-static equilibrium every time, look at what's happening dynamically. So not just what are the wrinkles at the end, but how do they actually form? Okay, and so I was a postdoc in Dominic Vella's group at the same time as this guy, Finn Box. And Finn's a really amazing experimentalist, and he did experiments that I would suggest couldn't be done, but he did them. Okay, and the first one he did was what we call dynamic impact. Okay, so he took that classical experiment and instead of indenting something very slowly, he fired a missile at the sheet. And so you see a much more complicated system than the ones in the previous slides. Okay, and you actually see two things. You see this ring that propagates radially outwards, and then you also see the wrinkles. And if you watch again in the next frame, the wrinkles don't just appear, they actually grow and coarsen as time goes on. So they start off very, very fine, and then they grow. Okay, so there's, I would say, a separation of length scales here. So there's kind of a global length scale, which is the sheet and this propagating ring. And then there's a second, much smaller length scale, which is the size of the wrinkles, right? And that separation of length scales is associated with some small parameter. And that small parameter basically quantifies the cost of energy, bending energy compared to stretching energy. So I could write that down in terms of actual parameters, but conceptually, it's that the sheets are very, very thin, and therefore their bending stiffness is very, very small. And that gives you a small parameter. Okay, so there's kind of two things to think about here. There's a circular wave, and then there's the coarsening of wrinkles. Since most people in this room are fluids people, the circular wave, I think, is maybe of more interest to you. So we'll talk about that and then just skip through the wrinkles afterwards. Okay, so this circular wave looks a bit like things you've seen, right? So you drop a stone in a pond, you have water falling from a tap. All of these scenarios, you have capillary waves that, or gravity capillary waves, whatever you want to call them, that propagate out from your point of impact. Okay, and the theory tells you that they always propagate out as a similarity solution in a certain parallel kind of way. And we thought ours was doing that, but it's the wrong parallel. Okay, so if you drop something and you have this front propagating radially outwards, and you don't have a sheet, then you see something that propagates like times to the 2/3. Perhaps 2/3. Oh no. Yes, okay, good. We're okay. 2/3. And what we saw experimentally was not t to the 2/3, it was t to the 1/2. And at first you kind of hope, well, maybe the experiments aren't very good and we'll do them again. And it's not that. It really is t to the 1/2. And if you remove the sheet and redo the experiment, you get t to the 2/3. Okay, so there's something extra going on here compared to normal impact problems. Over lunch, you mentioned Wagner theory. There's things in Wagner theory where a front or a wave or a impact propagates like t to the 1/2, but this is completely the wrong parameter regime for that, right? This isn't ship slamming. This isn't large inertia dominated kind of oceanographic impacts. This is just a wee little 1 millimeter metal ball falling on a little surface. Okay, so it's not Wagner theory, but it is also not the kind of calorimetric parallel. So what is it? It's something that's only happening because the sheet is there, and specifically, it's only happening because your sheet can have not just a uniform tension, but different tensions in different directions, and tensions that vary in space. So where did that t to the 2/3 come from? I don't think I have this in the slide. No, I don't. Where it comes from is you write down Bernoulli and you write down a stress balance on a surface, and you balance terms in the stress balance, and that gives you out this parallel. Okay, and in your stress balance on the surface, you have a gamma times curvature of the surface, more or less. Okay, and that gamma is just one number. But what we have is not a surface tension gamma, it's a stress tensor. And that stress tensor has a tension in the radial direction and a compression in the hoop direction. Okay, and before the sheet is wrinkled, that's a large compression and a large tension. But after the sheet is wrinkled, that compression more or less disappears. And it turns out if you write down the stress balance in the sheet and say there is nothing in the hoop direction, then the force in the radial direction has to have a radial dependence. Okay, so I guess in hindsight, I should have put in an equation, but if you try and balance all the terms in your surface stresses, but now you have a extra radial dependence in your stress, then it turns out that when you balance the time bits and the radial bits, you end up with a different parallel. Okay, and what's kind of neat about this is that you can write down a similarity solution, and that similarity solution has just one dimensionless parameter. For us, it falls out as a dimensionless sphere radius, but you can also think of it as a kind of modified Weber number. And so it takes you mathematically from one extreme where you have a point indenter to another extreme where you are back towards Wagner theory, so you have a very large impactor. But for us experimentally, we're in this regime where the impactor is quite small. Okay, I think that's all of the fluid mechanics I have in the slides. So if anyone wants to say or ask anything, now is a good time. Yeah.
These are the impactors.
Yeah.
Relative to what, the sheet or like?
Yeah, good question. So relative to, it's not just the sheet, it's like pillar length.
Waves that can.
Yeah. Yes, yeah. Where that capillary length now accounts for the tension in the sheet as opposed to just surface tension. Yeah.
Small thing,
Yeah.
the sphere, it
Yeah.
does break the sheet, so it does go through like a hole,
No,
doesn't it?
No.
I'll keep listening then.
So, yeah, I mean, there's a region around, like, very close to that indenting sphere where all of this breaks down because you have large stretching, you probably have some damage and various other complications. But once you move a tiny bit away from that kind of contact zone, which we didn't calculate, we just assumed it was something, then it's this similarity solution.
Mathematically, how do you model, like, do you start from your flat sheet and then you deform it, or you start from like the maximum deformation and you see how it goes back to a sort of equilibrium position?
The first one.
The first one, so you start from flat and then, okay.
Yeah, and so I guess something to say here is that the theory is all linearized, so we need small deflections, small angles for this to hold.
Okay.
Yeah.
Okay. And can it be think, I mean, how important is for the 2 to the 1/2 flow to be a two-dimensional model, or can it be a one-dimensional model, for example?
It has to have radial symmetry. You have to have
Okay.
a circular setup. Yeah, if you did, if you say had a sheet and a bar come down on it, you would expect to be back to 2/3. It's only because you have something that is a tension that looks like 1/r, basically. Yeah. Yeah.
So the sphere comes in with some impact velocity. I think I'm trying to get my head around the regime. So is it treated as a constant velocity at the more invisible time? That's all you're really looking at, this t to the half.
Yes, and then once it slows down, the equations still hold, but you no longer have a similarity solution.
So for the timescales that you were looking at, it's just a constant velocity.
Yeah, and then it all breaks down later. Yeah. Cool. What time is it? Okay, so I will tell you a little bit then about modeling the actual wrinkles. But feel free to jump in at any time. Okay, so maybe I can just remind you kind of the big picture of this experiment and what we're trying to do. So we're floating a sheet of subelastic material. We're dropping an impactor on it that's pushing the sheet down, moving stuff radially inward. And so a material circle that used to have some radius r is now it's a reduced radius. So you have compression and wrinkles form. Okay, and I have this small parameter associated with the fact that the sheet's very thin and has a very small bending stiffness. And what we looked at with that similarity solution is leading order behavior. And then the wrinkles appear basically as a higher order correction to that. So they're on a smaller length scale, but they also have a much smaller amplitude. And so maybe it's not surprising that they appear as a higher order correction, but it also happens naturally if you write down asymptotic expansions, substitute them into your governing equations, and crank the handle. Okay, so then the question is, what affects the wrinkles? Okay, so before I started by talking about an Euler beam, and I had a 1D thing, but I had a bending stiffness times a fourth derivative, and then I had a tension or compression times a curvature. Okay, and so if you're in 2D and have a stress tensor instead of just a force, then those terms become these two terms. Okay, and then when we moved to my sheet floating on water, I put in a buoyancy or a substrate stiffness term. Okay, but that's not going to be important until I lift up some non-trivial amount of liquid. So the third effect that actually matters in the time-dependent version of the problem is fluid inertia. Okay, so conceptually, if you want to move fluid on a very short time scale, you have to accelerate it. And if you then ask, well, how big a wrinkle can I make? That's basically limited by how quickly you can move fluid. Okay, so the length scale of the wrinkles is the length scale over which you have a balance between the stresses in the sheet that are trying to drive buckling and the inertia of the fluid underneath that says, hang on a minute, I was over here and now you want me to be over there. Okay, and so I've been talking about my small parameter in very loose terms so far, but in this particular problem, the small parameter is bending stiffness divided by rho v squared, so that's from my inertia term, times this length scale cubed. And that's much smaller than 1. And that gives you this separation of scales. So that's basically why the wrinkles happen over a much smaller length scale than anything else. Okay, so if you think about these terms, I have bending times a fourth derivative. And then if I'm differentiating in the radial direction, things are changing slowly. But if I'm differentiating in the theta direction, then I'm going up and down and up and down and up and down this rapidly oscillating surface. Okay, and so even though B for my bending stiffness is small, I'm multiplying by a derivative of something that's highly oscillatory, and I promote this term back up to balance with my compression term. Okay, and so that's why the bending stiffness doesn't matter for the leading order behavior because that's just an axisymmetric propagating wave, but it's really important for the wrinkles because they're highly oscillatory. Okay, so from a modeling point of view, we basically took this force balance and all the boundary conditions and whatnot that you need to go with it. And we thought about having a solution that isn't just a sign, it's a sum of signs, so sum of Fourier modes. And then you ask what is the amplitude of each of those modes as a function of time. And then you can predict what is the dominant wavelength at any moment in time. Okay, and so it turns out that that dominant wavelength increases in time with a particular power law. And so this is really important because the original quasi-static experiment said that the more you indent, the finer your wrinkles get. And here, because we have dynamics happening, even though we are indenting more, we are actually seeing our wrinkles get coarser instead of finer. Okay, and that makes sense conceptually because basically if you want to form wrinkles, then you have to move liquid. If you want to move liquid, you have to fight against the inertia of that liquid. So you basically have to start with very small wrinkles and then build up gradually. And so in these dynamic problems, fluid inertia plays the role of a stiffness, a competing stiffness, whereas in static problems, you would have had buoyancy playing that competing role. Okay, I like that you guys are interactive, so now I'm just looking out hopefully in case anyone has a question. Maybe I can take 5 minutes to say something about following on from this, if that's okay. Okay, so all of this was about trying to understand something to do with dynamics and how wrinkles form. And it turns out all of the dynamics are controlled by the inertia of the underlying substrate. So the dynamics are not really anything to do with the sheet itself in some ways. You know, you could change the sheet and you won't change the driver of the dynamics. So then we tried to come up with a system where the dynamics of the wrinkles would be due to the sheet itself. And the way you do that is to get rid of the substrate. If you're a mathematician, that's fine. If you're an experimentalist, that's harder. But Finn is an uber experimentalist. So he got rings or annuli of elastic material. He floated them on a soap film. So we had soap film inside and outside of the ring. Then he broke the outer part of the soap film. So now you just have something that's a ring, soap film inside. So stuff gets pulled inwards. However, it's no longer held up, so it's falling. And as it's falling, he images it. And he sees these beautiful wrinkling patterns. Okay, so if you think about an elastic ring, like an elastic band, right? You can make a figure of 8 shape out of that, but you would never see anything more symmetry than a figure of 8 shape unless you use all of your fingers to hold bits of the ring in place. But what he sees experimentally is that you can obtain these higher modes because of the inertia of the ring. So it takes time to make a figure of 8 mode, and you can do that over a long time scale. But instantaneously, if you just take something and pull on it really hard all at once, then it will try and buckle everywhere all at once. And so you will initially see highly oscillatory modes, which gradually coarsen. And so from a modeling point of view, it's actually quite similar to the last problem, but instead of substrate inertia, now you have the inertia of the sheet itself. Okay, so that's everything to do with varying in time. There's also a question about what if you vary in space. So this is ongoing work with Dominic Oxford and some colleagues in UMass Amherst. And this question of varying spatially really matters, because if you have something that has a fixed wavelength but is circular, then you need more wrinkles at the edge than in the middle. And so you need to have some branching. But also, if you have something where you have a substrate and the substrate stiffness is varying, then the preferred wavelength is going to vary in space. And so what we've been doing is thinking about kind of a prototypical problem where you have a rectangular elastic sheet, so something like this, on a planar substrate, so everything is flat. You're going to push 2 ends together and make a wrinkle. But what I'm going to do is have different substrate stiffness at one end of the wrinkles than at the other. And so I'm going to have a system where I have, say, a desired wrinkle pattern with 4 wrinkles on one side and maybe 20 wrinkles on the other side. And the question is, how do you get from 4 wrinkles to 20 wrinkles? And the answer is it depends on tension. Okay, so we started out by doing simulations in Surface Evolver, which is finite elements, open source software. And so we can look at a top-down view of a simulated system where I have 4 wrinkles on one end and 20 wrinkles on the other end. And you don't see a whole lot besides knowing that it does actually go from 4 to 20. Okay, so it's helpful to maybe think about taking that profile and breaking it into Fourier modes. And so you have first Fourier mode corresponding to 4 wrinkles, and then the amplitude of that decays, and the one corresponding to 5 wrinkles increases, and you tip through all of the Fourier modes. Okay, and then what we're doing as you come down the slide is we're increasing the tension in the sheet. And if you do your non-dimensionalization correctly, then you see that increasing the tension is analogous to changing how rapidly the bending stiffness is changing. Okay, so in this bottom one, you basically stretch out the whole system. And because of that, you have more Fourier modes present at any one point in space. And so if you can take the results of simulations and Fourier transform, you can also take the governing equations and Fourier transform those. And so just like in the dynamics problem where we had many Fourier modes and their amplitude was evolving in space, here I can have many Fourier modes and their amplitude evolving in time. Yeah, and there's various bits and pieces that we're doing in this space. But yeah, I guess the kind of interesting thing to say is that there is this special dimensionless number that quantifies the importance of the size of this gradient in substrate stiffness compared to the bendo-capillary length scale, if you want to call it that. And there's just that one parameter basically. And so you can vary that and see all possible configurations. So increasing tension or changing the substrate gradients are comparable. Although I'm not confident my arrows point the right way. Okay, so that's varying in space. And then the new work that is hopefully starting this year comes back kind of to your question about whether you break the sheet. So everything that we've thought about so far has been elastic. And most people, most of the time in this field, think about elastic sheets. But even in these experiments, when we looked at the sheets after using them, we saw plastic damage, not just in the middle, but also where the cusp of the wrinkles had been particularly sharp. So one thing I want to think about is that transition to plasticity. When do you start seeing damage? When do you start to see permanent deformation? Then something that for me naturally follows on from that is to go back to this method spinning problem, because there you have a combination of elastic and plastic deformation, but quite a bit more plastic deformation than in the first case. And then the third thing that works in terms of my interests to think about is to go back to the glass drawing problem, because there you have a sheet where you have tensions and compressions and wrinkling, but it's a viscous sheet. And so what I want to do is figure out if you can take some of the framework that now exists for modeling these elastic systems and adapt some of it to start thinking about other materials. And I put a shameless plug because I have money for a postdoc who we've hired, but also for a PhD student, and I'm finding it really hard to find a PhD student. So if you guys have anyone in your final year or master's courses who you think might be a good fit for a fluid mechanics modeling PhD, I'd be really grateful if you could pass on the details. And that's all from me, and thank you. Yeah,
You have an elastic band with a soap film that's initially held in a circle and then
Yeah.
basically released.
Yeah.
And then what do you see happening?
okay, so the elastic band has soap film both inside and outside.
Yeah.
And you break the one on the outside, and so then you have something like a pressure internally that pulls everything
Yeah.
basically inwards. And basically, as you vary the dimensions of the ring, you see different numbers of. Thank you, yes. So you see different modes. And so from a modeling point of view, all of the modes are growing, but at different rates. And the rates that they are growing at changes. So the mode that you see is to some extent a function of the timescale you're looking at. And the timescale we're looking at is the timescale on which we can visually see the mode. So in principle, if you could detect very, very tiny deformations to the elastic mode, you would see some much higher order buckling. And we're just looking at the time we can look at it and then modeling that part of the problem.
So what goes into the modelling? I mean, you've got, there's classic papers on the extensive elastic ring with the pressure inside. And the mode that looks like that is always the most unstable.
Yeah.
So what extra ingredients have you got there? Do you have to worry about sort of fluid transport in the film? Or,
And it's the inertia of the ring.
and the inertia of the elastic bit?
Exactly, yes. So you're not in like quasi-static equilibrium anymore. And that, I think, basically is the difference. Yeah.
Quick question if you can. When you have the film on the surface of the water,
Mhm.
you assume that the fluid beneath work with no slip condition.
Yeah.
So it basically moves the same way up as the film.
Have we? No, we've actually just neglected any shear forces. And that's probably not perfect, but it's obviously.
Okay.
Yeah.
Could you just explain when you talked about how you linearized one of your problems? What was it that, when does that break down? Could you just explain that again, please?
Yeah, of course. Okay, so even before you do any of. Where should I start? Okay, so. You normally would do linear stability analysis on a system where you kind of buckling. And so there your small parameter is the smallness of the perturbation. If you try and do that here, you make predictions that completely disagree with experiments. And there's a reason to do that, for that to do with the stresses undergoing large changes, and so you're not having a small perturbation. So then you need a different small parameter, and that small parameter turns out to be this smallness of the bending stiffness. And people call that a far from threshold regime as opposed to a near threshold regime. So when you're in that regime, or if you want that regime to hold, then you need the thickness of the sheet to be incredibly small. But you take that small parameter and you apply it to a system of equations that only holds if your sheet is almost planar. So you can't have like a height evolving along an arc length, you have just a height that evolves along X.
So you're taking like a ball or something like that, again, that's the compression.
Yeah.
Is there a critical sort of distance that it can deflect? Does that have like a constraint on the time for how long before it goes too deep in, for the
Yes,
amplitude to be too large.
yes, 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 yes. So there's a window where you've deflected enough that you've induced enough compression to get wrinkles.
Yeah.
But you haven't deflected it so much.
So that's what I was.
That
wondering.
everything
Yeah,
is
okay,
there.
right. So,
Yeah. And this is basically why you need your sheet to be incredibly thin, because if your sheet's incredibly thin, you only need a very small amount of compression to get wrinkles. Yeah, yeah,
Cool,
yeah,
thank you.
that makes sense.
Okay. We can thank Doireann again and have a discussion at the table. Thanks again.